So in this video, I share information that I use in my Chemistry 1220 course when we're looking at sections 19.5 and 19.6, Gibbs free energy, and the Gibbs free energy and temperature. Uh, this is really a central idea if I want to understand how Gibbs free energy and thermodynamics explain spontaneity. So this is really something that has a lot of information conceptually, I would say, for the teacher. Some of this information is shared with the student, but in terms of big picture, this is one of the most important ideas, perhaps the most important idea that I have the entire year. We end up using it for some various calculations, and there's a conceptual understanding that goes with it. But this is really, if I were to say, what is the most important uh, lecture I have the entire semester, it's probably this one for my own understanding. The idea of connecting it to the equilibrium constant, that's the topic of non-standard conditions. That's something that I say for another discussion. So I've mentioned how the Gibbs free energy, really important. This is how I understand for myself and explain to myself whether a process occurs, whether it's a physical process, chemical process. This has become now my guiding principle. How about for you? Is Gibbs free energy important for your own understanding? Share with me your thoughts. So, information then I'd share with my class as we begin to apply this. So here's a reaction, the Haber process. I show the delta H under the standard conditions for the entropy change. Entropy is going down for this reaction. And then we use this to apply a few different ideas. Would you have predicted the entropy decreases? Can we calculate the value for the hydrogen gas and compare it to ammonia and nitrogen gas? And what do we know about the entropy for the surroundings? So these are good sort of reviews, discussion points. Yeah, I would be saying that moles of gas decrease, so I'd expect the entropy to go down. We can calculate the value for the H2 because we know the overall entropy change. So we can calculate for one of the internal values. It makes sense. It's similar to N2, but it has a lower mass. It's less complex than NH3. It has a lower mass. This idea of how the mass affects the entropy, that's something that's explained using quantum mechanics in the 1220 course. We just sort of take it as a detail, as a fact. In my honors course, we look more closely at why the mass is important. The entropy goes down. If this reaction takes place, what does it tell me about the surroundings? It tells me that this must be an exothermic process, and the entropy of the surroundings is increasing because it's exothermic and heat is going into the surroundings. I know this because the entropy of the system, this particular reaction, is going down. All of these important ideas, calculations, and concepts for the class. So if we think now about the Gibbs free energy, this is just another way of describing the entropy change for the universe. The entropy change for the universe includes both the system and the surroundings. When the entropy is going up overall, it's a spontaneous process. So we might ask, well, how can we possibly calculate the entropy change for the universe? Is that just an abstract idea? I mean, put an ice cube in your hand. It will spontaneously melt. What is that doing to the entropy of the universe? Can we really calculate that? It turns out we can. Amazingly, we can. So let's see how we get at that idea. So I put in red here, this is information I usually would share on the board and we talk through. So back to Clausius' description, our change in entropy involves the heat that's being transferred and the temperature of that transfer. So let's consider then the heat. If it's entering the surroundings, it's leaving the system. So by putting a negative sign there, I take whatever description I have for the system, and now I'm thinking about it in terms of the surroundings. If it's exothermic for the system, it's endothermic for the surroundings. So by putting a negative sign in front of the heat as I'm thinking about it for the system, I'm now thinking about it for the surroundings. second thought is a lot of times when we're thinking about the heat, we're thinking about enthalpy. We're thinking about the heat that's being transferred at constant pressure. So for an exothermic process, heat's leaving the system. The entropy of the surroundings is going up. If I think about that entropy change in terms of the surroundings, a lot of times I sort of put it in double brackets here. The negative tells me, okay, take whatever's taking place for the system and now think about it in terms of the surroundings. So if it's exothermic for the system with a negative sign, a negative and a negative tells me the entropy change for the surroundings is going up. This makes sense. Heat is leaving the system, and now the entropy, the entropy of the surroundings is increasing. So let's see now as far as how this fits mathematically. So we have our first description here that the system, the surroundings, gives me the overall entropy of the universe. And when that goes up, spontaneous. Let's substitute in a description for the surroundings by thinking about it in terms of the enthalpy for the system. We have a negative sign in front of it because we want to think about it for the surroundings. But all we've done right here is we now have an expression in terms of the enthalpy change for the system and thinking about what that means for the entropy for the surroundings. Let's now just adjust the terms. Switch around these and I have the system entropy minus the h over t term. Everything is still the same. If this ends up being positive, it's spontaneous. If this is positive, this means the entropy for the universe is going up. If we continue to rearrange terms, all we're going to do is bring the temperature that was in the denominator, instead of having it below the enthalpy, we'll put it so it's attached to the system. And we're also going to end up changing the sign on that. We're going to change the sign on this, and we're going to say, instead of having this value be positive, meaning the entropy of the universe is going up, by switching these terms and changing the, in a sense, multiplying the whole thing by -1, now when this value is negative, that means the entropy of the universe is going up. We're going to call that the change in the Gibbs free energy. This is how we derive our expression for the Gibbs free energy. All we have done is taken this expression right here. We've thought about what does it mean to change the entropy for the surroundings, and then we just adjusted the terms. That's all that we did within that. The entropy change that we have for the surroundings is in terms of something involving the system. This is a really powerful idea here. This is how we can calculate the entropy change for the universe, because we have it in terms of something that we can measure for the system. I can't put a thermometer in the entire universe, but I can put something in the system. I can make measurements for the system. That's what the Gibbs free energy is doing. In a brilliant way, it's thinking about things that we can measure for the system and asking, what does that have now as far as implications for the surroundings? And notice our expression here. If the temperature is small, the entropy increase is larger. This is just Clausius' description. Remember, he had heat being transferred over the temperature at which that took place. This is just the same thing that we have right here. When the temperature is small, for the same amount of heat, the entropy change will be larger. So when we have this expression right here, our Gibbs free energy one, it's not a fancy derivation. All it is doing is saying that we have an enthalpy change over a particular temperature for the system. This has implications now for the surroundings, and then we take that temperature term and we just slide it over here. We are learning about the universe, but we only make measurements for the system that is at hand. That's a really powerful idea. I find that when this temperature gets switched over here, in some ways, it loses the insight that that temperature was really in terms of how it was involving the enthalpy change for the system and what that meant for the surroundings. What questions do you have on this? What questions do you have of how we put together the entropy change for the system and the surroundings, and we're now using that to describe the entropy change for the universe? So here we have provided data, thermodynamic quantities, enthalpy, Gibbs free energy, and entropy. We can do calculations with these where we're doing final minus initial. We can do that for all of these different terms. Now, when I look at these, some of these are being defined as zero. That's, remember, if we do our standard enthalpy of formation or our standard Gibbs free energy of formation, those are defined as having values of zero. When I look at these other ones, in addition to being able to do calculations, how do I begin to sort of make sense of these? The more negative the value, the more favored it is in terms of the Gibbs free energy. And the Gibbs free energy is the part that counts. I mean, in chemistry, a lot of times we use this word stable. I think we mean different things by it. I mean, sort of teacher to teacher here, what is more stable? In a sense, when we began the class and we were thinking just in terms of the enthalpy change, we could think about things being more stable as they move to a lower potential energy. But now we've just dramatically changed our storyline. More stable is not simply in terms of the enthalpy change. It's combining the enthalpy change for the system, the entropy change for the system, and how that first enthalpy change and the temperature at which it takes place is really about the overall entropy change for the universe. The overall entropy change for the universe, that's what I'm thinking about with Gibbs. And that's what is leading to something being more favored. Is it leading to a larger entropy change for the universe? When we look at a description like this of a reaction progress diagram, grab this one from an organic chemistry book. Notice when it's saying energy, the energy is in terms of the Gibbs free energy. When we talk about something being more favored, it means the entropy of the universe has increased the most. That's why I say this is my guiding principle for explanations. Increases in the Gibbs free energy means increases in the entropy of the universe, and that's what is the direction our world is heading in. Now, if we look at the temperature dependence of this, I had the students, first of all, predict the sign for these entropy changes. They usually do pretty good with that, if we have our different phase change, or we see a difference in the moles of gas. I then add in the information. I'll tell them that that first one is exothermic as written. So therefore, the reverse one must be endothermic. And we use that then to put together our sign conventions here. We discuss then the implications for this, whether this means something spontaneous at all temperatures, non-spontaneous, or if there's a temperature dependence. And we're connecting it back to this expression. We want to be able to look at the temperature dependence or connect the temperature dependence with what that tells me about the enthalpy and entropy changes for the system. Now, teacher to teacher, most common is a temperature dependence like this, meaning there is a particular temperature at which something becomes spontaneous, something being spontaneous at low temperatures, something being spontaneous at high temperatures, and non-spontaneous otherwise. That there is a temperature dependence like this. This is what we typically find in nature. So if I want to think about this, matter is attracted to other matter, it moves closer together. That's describing an exothermic process. As it's moving closer together, the entropy is going down. Notice that we have two different terms here. Exothermic being favorable for the that particular reaction, but the entropy is going down for the system. Or we can imagine just the opposite. The matter is moving further apart, entropy is increasing, but what caused it to move further apart? A lot of times that's because it's an endothermic process. So these cases right here, this is what we often find. Is it possible to have it exothermic and the entropy increases? That is possible. This first example here of a chemical reaction written that way describes that. But in many cases, that's not as easy to conceptualize. In fact, those are, it's not easy to just say, oh, well, let me just always grab examples for those. Usually what we have is, like I mentioned, these ones that are spontaneous at a particular temperature, whether it's high or low. What are your thoughts on using these sign conventions? Is that something that's important? Can you understand why we typically have this balancing of being favored in one of the terms and unfavorable in the other? So if you have then this temperature dependence, you have a point, a temperature at which you're going to reach equilibrium. We know that we have, for this phase change, H2O solid and liquid, there's a temperature at which that reaches equilibrium. What that means in terms of the setup right here, the change in the Gibbs free energy, it has a value of 0. It doesn't have a tendency to go at that particular temperature in either direction. This right here, this is a huge conceptual idea. When the Gibbs free energy is 0, you've reached equilibrium. It doesn't have a tendency to move either more to the left or more to the right. You've reached equilibrium. This is going to be extremely important for our explanations. We want to consider, what does it mean to have reached a point where we're now at equilibrium? If we're going to use the Gibbs free energy, if we're going to use chemical thermodynamics to explain phenomena including equilibrium, we have to have a strong description of this, strong conceptual understanding. We can easily do the math for that. We can solve for the particular temperature where that takes place. And notice if we put in our values right here, sure enough, this would be our freezing point. This would be our melting point. We're at equilibrium for H2O. I like to work this example because it leads us to a number that the students would have predicted. We want to be able to do calculations like that. We could even take it for something like this. This is a demo I often use. Hydrogen plus oxygen balloon, bring a match to it, a big kaboom. The heat and the cooling is not great in my room, so I say it's often hot in this classroom. At what point would this reaction no longer be spontaneous? At what point would our Gibbs free energy equal 0? So we could plug in our terms and find a temperature at which this takes place, or we've reached equilibrium. So this is now a really cool idea, because this sure seems like a reaction. I mean, it's an explosion that it would always be spontaneous. But you can have a high enough temperature, and 5,000 degrees is not crazy. Temperature of the sun is going to be 5,000 degrees Kelvin. You can have a temperature, now maybe that is crazy, but you can have a high enough temperature where this is no longer spontaneous. This reaction is no longer increasing the entropy of the universe, because the surroundings are at such a high temperature that even if you put more heat in there, it's really having a very small increase for the entropy of the universe. And the fact that the entropy of this reaction is going down, you're no longer going to have a tendency for it to take place. This idea conceptually of having a temperature at which something is no longer spontaneous, powerful idea for us. Let's make clear that when we're talking about thermodynamics and explanations, we're not talking about the speed at which something takes place. I use this example here for our thermite reaction. We have our different terms right here. This ends up being spontaneous. We have a negative change here for our standard Gibbs free energy. It's an exothermic reaction. We saw the entropy was going down, but it's very exothermic. How about this one? So I have a unknown reactant, reacts with oxygen to form CO2. For this reaction, it also has a negative value for the Gibbs free energy. This is looking at what happens to diamond. Diamond, carbon in the form of diamond reacting with oxygen to give CO2. Have we ever seen that take place? Well, it's really favored in terms of the thermodynamics, but it's not something that we see occur. This idea that something can be spontaneous, doesn't mean it's going to be fast. It doesn't mean that it rapidly occurs. Recall that when we're looking at thermodynamics, we're interested in where we start and where we finish. Kinetics, that's the in-between part. Kinds of problems that we can practice and apply for this. We're looking at ones where we're having different values and interpreting them in different ways. I like this bottom one here because we have some data now where we see something's being exothermic and the entropy goes down. I'd like to be able to think about those entropy changes. Are those predictions we would have made? And we see that we have examples exothermic and the entropy goes down, endothermic goes down, endothermic, and it goes up. So I think these are really good to think about. Here's another one where we're doing a calculations and we're thinking about it at a different temperature. So within this section right here, Gibbs free energy and its relationship to temperature, central, I think, to any of the explanations that we want to offer. The feature we haven't talked about, though, is what does it mean if we're at non-standard conditions? Temperature is a factor that can affect whether a reaction, a process is spontaneous. Non-standard conditions is saying, well, how are the amounts important? If we want to think about the equilibrium of a chemical reaction, that's something we need to consider as well.